So clearly the take-home message there, whether you believe the numbers or not, the take-home message there is there is potentially a lot of value in the data when implemented on a large scale. Why do I highlight that? Because in Alberta, you guys have been pretty proactive in terms of adopting LiDAR on a pretty large scale. And so what that means is when you adopt it on a large scale, there are potentially a lot of benefits because the community is very large, and you can leverage a lot of resource into realizing those benefits. Okay, so now to the technology piece. So I find this one a little bit dry because it tends to lose people a little bit. So I'll try and keep it as interesting as possible and not get too stuck on the technology. Because I actually find this stuff exciting, but the problem is I know a lot of people don't. So it's difficult for me to find that middle road. Anyway, so it's all about this point B. We're trying to measure a coordinate on the ground. In fact, we're trying to measure hundreds of thousands of coordinates on the ground every second. How do we do that? Well, as I'm sure you all know, in order to measure a coordinate on the ground from an aircraft that's potentially a few thousand meters above the ground requires quite some sophisticated measurements. And there are essentially 4 measurements that need to be made. First of all, we need to know A, the position of the origin of that laser pulse on board the aircraft. We also need to know the range or the distance between the aircraft and the ground. Because we're doing scanning systems, we need to know the scan angle at the moment that pulse was emitted. We also need to know the attitude of the aircraft. So those are those 4 components, and obviously the equation to derive the coordinate B is a lot more complicated than B is a function of A, R, theta, omega. That's just for the sake of illustrating that there's 4 important components that we need to pay attention to. And that's as complicated as the math's going to get today. I'm not going to go any deeper into it. So what do these systems look like? Now I'm a little bit biased. I used to work for Optech Incorporated, but there are a lot of other LiDAR manufacturers out there, especially today. 10 years ago there weren't that many, but today there's quite a few LiDAR manufacturers out there. But anyway, I apologize. I do have a little bit of Optech bias because I used to work for the company. I'm not on commission, so I'm not trying to sell their systems or anything like that. But anyway, this is the suite of airborne laser scanners that they currently market. I guess you could argue that the 3100 is not exactly obsolete, but it's not something that they sell anymore. The Gemini is probably it superseded the 3100. This is the system that we owned at the AGRG for 7 or 8 years, and so I'm mostly familiar with this particular unit. But over the last couple of years, they've introduced the Orion and the Pegasus. So these are the more contemporary LiDAR systems. I won't go into the specifications of all of these systems, but what I will do is just give you an idea of the range of technical specifications for these things. So even though those sensors all vary in terms of their specifics, we can say that the data capture rate can be up to 500 kilohertz, or 500,000 emitted pulses per second. And for every one of those emitted pulses, we can capture either a full waveform response, or we can capture, for these particular systems, up to 4 returns. So in theory, what that means is if we're emitting 500,000 pulses, we can capture up to 2 million measurements of the terrain and what overlies the terrain every second. In reality, that probably doesn't happen very often, but it's potentially the upper limit on data capture right now for an airborne system. They tend to operate in the near infrared. So that would be 1064 or 1500 nanometers, or so near infrared, just outside of the visible. Typically plus minus 30 degrees or thereabouts is the scan angle, so a full field of view of 50 to 60 degrees. Now that's variable. Most surveys aren't deployed at a full scan angle, and the reason for that is because the geometric problems at the edges of the scan, or when you're trying to penetrate canopy, you don't want a wide scan because it's going to be hitting sides of trees as opposed to the ground. But nonetheless, if you're flying over the desert, why not? Widen it out, fly as wide as you can. So that's the range of scan angle capability. Now there are systems out there that can fly higher than 4,000 meters. But 4,000 meters seems to be a typical upper operating ceiling. You know, one of the reasons for that is we often want to stay below the clouds. We want to minimize atmospheric effects. The higher we fly, the greater we propagate errors into the final solution. So there's a lot of advantages to flying, you know, closer to the Earth's surface. But at the same time, fly higher, you can cover a lot more ground more quickly. And of course, they all capture the point coordinates and the signal strength or the intensity. But it's becoming more and more typical to fuse these systems with other sensors. Obviously, standard RGB cameras. We've been messing around a lot with thermal, integrated LiDAR and thermal imagery. That has a lot of potential. It's actually kind of cool to look at 3D thermal imagery. LiDAR and hyperspectral. I know Olaf Niemann's here, at least tomorrow. We'll be talking about that type of thing. Okay, so we've seen what one of these things looks like. We know that there are 4 measurement components. So let's look at a schematic diagram. I've mentioned that there are 4 primary measurements. We need to know the position. We get that from GPS on board the aircraft. We need to know the orientation of the sensor. So we can use an inertial measurement unit for that. We need to know range. Range is what we get from the LiDAR. So see, LiDAR is really only one piece of the puzzle. It's an important piece, but it really is only one piece of it. And we need to know scan angle. Now, in terms of the way the systems are integrated, the GPS and the IMU gives us position and attitude. But these 2 measurements aren't made individually. In order to get the most accurate position and to get the most accurate attitude, the GPS and the IMU systems effectively need to talk to one another. There's a company in Toronto, Planets, that have pioneered the development of these position orientation systems that integrate GPS and IMUs. And so this is the kind of technology that we typically find within an airborne laser scanning system. And incidentally, it's probably worth pointing out that it wasn't until we had accurate IMUs integrated with GPS that airborne laser scanning was possible. We had LiDAR before that. LiDAR's been around for quite a while. But we weren't able to deploy them on aircraft in such a way that we could capture accurate terrain models until we had this really accurate positioning and attitude technology. So really, that was the technology that facilitated airborne laser scanning. Of course, we also have the laser scanner system. Now, if we decouple the laser scanner system from a position orientation system, we essentially have a terrestrial laser scanner. They look a little bit differently, but the technologies are pretty much the same. You know, the specifications might be different, but essentially a terrestrial laser scanner is a LiDAR and a scanning system. Slightly different configuration, but fundamentally the same technology. Put it all together and we have an airborne laser terrain map. So just a little bit more information on each one of those 4 primary components. The GPS. So I like to consider the GPS as the technology that gives us the trajectory from which we can hang the rest of the solution from. So it all starts from a GPS trajectory. So to illustrate that, what we see here is a number of flight lines. So the red points illustrate measurements captured, well, in this particular case, probably every few seconds, but in real time, it's usually every half a second that we capture GPS measurements. And then beneath that, we can see a digital terrain model. But that digital terrain model is made possible because we've got the trajectory and we can hang all of the other measurements on that trajectory. Now, the GPS data collection is fundamentally important, and we have to get it right. I'm not going to go, I mean, GPS would be a whole lecture in itself, so I'm not going to get into any detail on this, but I just want to stress the importance of accurate GPS. We need to have good ground control. We need to collect data during, optimal windows. We need to be cognizant of interference with the GPS. Operationally, there's a lot of ways that the GPS can go wrong and compromise the entire survey. So it's something that the operator, the service provider, has to be very, very careful on. Just anecdotally, for example, we've installed in aircraft in the past where we've had GPS problems, and we've been scratching our heads as to what the problem was, only to find out that it's because the aircraft we were in had some kind of short circuit on one of their radio systems. And because they had a short circuit on it, every time they would talk to air traffic control, we would have a data gap. And things like that can take a little bit of a while to troubleshoot and work out. But nonetheless, it's critical to the overall solution, so it needs to be paid attention to. The inertial measurement unit. So this is the IMU, little black box, about yay big, located as close as possible to the pulse origin, or the mirror, on the scanner. And that measures the pitch, the roll, and the heading of the aircraft. So as the aircraft is moving through space, its three-dimensional attitude is measured very rapidly, typically a few hundred times per second, and that's measured by 3 accelerometers and 3 gyros. So we can measure the movement, and we can measure the attitude changes. And of course the LiDAR. We tend to think it's all about the LiDAR, but the LiDAR is just one component. And it's all about time. So a pulse is emitted, hits a target, returns, and what we're trying to measure is the round trip travel time. So in order to calculate the range, we multiply that round trip travel time by the speed of light, divide it by 2, and that gives us that distance. So time is the critical parameter. Now this is where it can get really dry, so I'm not going to dwell on the actual laser physics component too much. But typically, in airborne systems, use semiconductor lasers with a near-infrared beam. We don't have to use near-infrared, but there's a lot of practical considerations that make that suitable. Highly directional, highly collimated. Has to be highly directional in order for us to get an accurate measurement at the ground level. Has to be highly collimated so that the pulse doesn't spread out and become massive by the time it hits the ground from 4,000 meters up in the air. When that pulse encounters the ground surface, or whatever's above the ground surface, it returns as a waveform. Now, to capture an entire waveform requires a lot of data storage and very fast processing in order to digitize and capture that entire waveform. So, for practical purposes, it's usually converted to discrete points, and that's done in real time using a time interval meter. So here's a schematic of what happens to the laser pulse as it passes after it's hit the ground and reflects back to the system. It goes through a filter to make sure there's no noise in there. It kind of filters out all the other wavelengths. Passes through an avalanche photodiode. The avalanche photodiode converts the light energy into an electrical or a voltage signal. That voltage signal is passed into a constant fraction discriminator. That CFD, constant fraction discriminator, allows the waveform to be time tagged, and then that passes into a time interval meter. And the time interval meter stores the emission time and the reception time for all of those pulses, and then that information is stored goes into the processor and is stored on a hard drive. And I'll leave it at that. The scanner system is what redirects that pulse. As the pulse leaves the aircraft, it has to be redirected across the ground so that we can capture a whole swath of data. So that's kind of done in series. As the pulse hits the mirror, it flies down to the ground and back again. The mirror moves along a little bit, another pulse hits it, and then it moves to an adjacent point on the ground surface. And there are various different types of scanners. I'm not going to go into the different designs of scanner mirrors and what the pros and cons are of each one. Just suffice it to say there are a number of different types out there. They all produce slightly different patterns on the ground, and there are pros and cons associated with each. But the 4 dominant types are the oscillating mirror, a nutating mirror, a polygon mirror, and a fiber scanner. If anyone's interested in any of that stuff, we can talk about it later. Okay, so all of these different measurements that are made at in different places in space. So the GPS is typically measured on the roof of the aircraft. The attitude is measured at the center of the IMU. The range is measured from the scanner mirror to the ground. Those are 3 different physical locations. In order to put all of this together and compute a coordinate of ground, we have to account for all of those offsets. So whenever we install a system in an aircraft, and in this particular example you can't see it, but the sensor is located aft, sticking out of a hole in the back of this twinotter. GPS is forward, a few meters away, and so we've got to measure the vertical offset and the X and Y horizontal offsets. And those are again, critical to ensure that we have an accurate solution at ground level. And I'm cognizant that time is running out. So this last section I want to focus on the point cloud. In some ways I could have started here. We've talked a little bit about applications, we've talked a little bit about the market, we've talked a little bit about the technology, but I think a lot of it's about the point cloud. And the reason for that is because the point cloud is a very underutilized deliverable from LiDAR systems. There's so much more that we can do with it. And so I just wanted to introduce the concept and maybe discuss briefly how we can leverage the point cloud into new applications. So here we see a cross-section through a forest stand. Again, this is that TerraScan software environment, which is on the Bentley MicroStation platform. So this isn't within a GIS environment, this is within a CAD environment. And I believe this is a 5-meter cross-section through a point cloud. So within that 5-meter cross-section, we can see there's a lot of points. The color coding here is just elevation, so there's nothing particularly interesting about the color coding here. Now this is the same point cloud, but the color coding is intensity. Now, what's interesting, at least I think, is we see a lot of high intensity returns at ground level, higher intensity returns in this shrub level, where we're only getting single returns, and some higher intensities at the outer envelope of the canopy. And we tend to see lower intensity returns in the middle of the canopy. Now, that is somewhat interesting or useful to point out, because it's common to believe that the intensity is a function of the reflectance properties of the material that the laser pulse encounters. So, for example, if we have a nice cut grassy lawn adjacent to an asphalt highway, the asphalt highway will come out dark. That nicely cut short grassy lawn or parkland is going to come out bright. And that's true, and the reason for that is because spectrally they have different characteristics. The grass is more highly reflective in the near infrared than the asphalt. So that's what we see. However, when we look at a forest canopy, we don't always see that. In fact, we often see that the forest canopy comes out darker. Not always, but often we see that the canopy comes out darker. And yet we know that that forest canopy is more highly reflective than the adjacent, bare earth or asphalt terrain that's nearby. Well, the reason for that is because the primary control over laser intensity is not the reflectance of the surface that it encounters, it is actually the contact area. Now imagine we have a laser pulse that when it encounters the ground, it's about that big. And if we're 2,000 meters off the ground, we're using an LTM type system, the pulse is probably going to be about that big. If that pulse encounters a nice flat surface, then all of that contact area is going to create a reflectance. And so all of that contact area, so we get a 100% response from that uniform area. So in that case, the intensity is a function of the reflectance of the surface. But in a forest canopy, that's not the case. What happens in a forest canopy is we get a pulse that's this big, but that pulse passes through the canopy. We'll get a little bit of reflection from high up in the canopy, a little bit of reflection from somewhere in the middle of the canopy, and if we're lucky, we'll get a little bit of reflection from the ground level. And at each one of those surfaces, the amount of intensity that's reflected back is a function of the contact area, and it's a function of the spectral reflectance. But primarily the contact area will be the dominant control. And so that's why we see in a 3D, in a profile like this, that's why we see higher intensities at ground level, even though the pulse has passed through the canopy, even though the ground level is quite likely of a lower reflectance than the leaves and the foliage above it. We still see higher intensities there because we've effectively got a 100% reflecting surface. Whatever energy makes it to that surface, we're going to get some kind of signal back from it. Whereas the foliage above it is only going to use a very small contact area. So we've just looked at multiple returns through the canopy. And this is one of the real virtues of contemporary airborne LiDAR, is that for every emitted pulse, we can get multiple returns. And so in this particular example, we see the edge of a building. So for a pulse that encounters the edge of that building, we'll get a pulse coming down, some of the energy will encounter the building edge, some of that energy will pass down to the ground, and we'll simultaneously be able to map the ground and the building. And so that's one of the values of a multiple return system. There are limitations, of course, though. If a pulse was to pass down and hit this podium and the floor here, we probably, in most cases, would not be able to capture the floor and the podium at the same time because the distance between them is too short. The time it takes for a pulse to travel from here to there is so short that the internal timing electronics of the system would not be able to distinguish between them. It would just see one return. But a building, of course, that is separated by several meters, the time taken is sufficiently long that the internal timing electronics can distinguish that. And I think the rule of thumb now is that the differences have to be more than about 1.5 meters before you can discern multiple returns. It differs by technology, but there seems to be a little bit of a hard limitation of 1 to 1.5 meters. Okay, so we have multiple return capability around buildings. That's very useful. We can capture building roofs, the ground, the edges of buildings. That means we can interrogate the point cloud. We can fit planes to the point cloud. We can look for, we can apply morphological rules. We can look for parallel lines. We can look for symmetry in the data. We can use some intelligent criteria to try to extract those planes or those roofs or those building sites and reconstruct models. So we go through a process of classifying the point cloud into these planes and edges and that kind of thing. And then we go to the next step of trying to vectorize those models. Of course, you could just rasterize the point cloud, but if anyone's trying to rasterize a point cloud over an urban environment, you end up with a lot of rounded edges and kind of noisy looking buildings, that kind of thing. But a process of classification and vectorization actually allows you to come up with a much more crisp and accurate building model from the point cloud. Here I've talked a lot about the canopy. We've talked a little bit about classification. I just wanted to illustrate the returns throughout a canopy here and the ground classification potential. So we know that LiDAR is primarily used for DEMs. There's a lot of other applications, but DEMs is probably the biggest one. The reason that LiDAR is so valuable in this regard is that it's an active sensor. We have this multiple return capability, and the returns can encounter and map both the canopy and the terrain simultaneously. However, of course, the conditions on the ground at the time of the survey dictate how good your ground model is going to be. In this particular example here, what we see is that we get a lot more ground returns when we're in leaf-off conditions. Makes perfect sense. And I mean, these numbers are just examples, but it's fair to think in these terms that when we're in leaf-off, we might be talking 60 to 70% ground returns. Dense canopy leaf-on, we might be looking to only get 30 to 40% ground returns. So of course, that's going to affect the data density. It's going to affect the amount of energy that is in a pulse when it comes back from the ground after it's passed through the canopy. If less energy returns, then the accuracy or the precision of that point is probably going to be lower. And so we get much noisier ground level models in a leaf-on condition. So there's a lot of reasons why we try to plan surveys for leaf-off conditions. So just to illustrate the ground classification, again, I could have a whole lecture on ground classification. So I'm really trying to go through this very, very quickly. So we've got a point cloud. This is what we're trying to get at, is this terrain model. For the sake of illustration, here's a tree. This is what the point cloud looks like over that tree. I hope that shows up okay. And then we run some kind of morphological filter. There's lots of different filters out there, but essentially most of them are based on some intelligent predictions about how the terrain behaves and how adjacent points proximal to one another, slopes and distances and that kind of thing. And then we run this iterative morphological classification to come up with a ground classification. So it essentially just separates the points in ground and non-ground. Now we've talked a lot about multiple returns. We've talked a little about canopy structure. I just wanted to illustrate this. There's more information in there than just the intensity. We actually know which returns are first returns, last returns, intermediate returns, or single returns. There's only one return from an immediate pulse. And so we can classify the data, or visualize the data, by the echo classification, or the return classification. And this is valuable because it tells us something about the canopy structure. I'll just separate out the first and last returns for an illustration here. First returns are blue, last returns are yellow. Now, I point this out because I hear time and again, you'll hear that ground classified data is often considered to be last returns, or last returns are often considered to be ground returns. I hear that time and again, and it's not true. What is true is that ground classified returns can be extracted from last returns and or single returns. But as this slide illustrates, we can also get last returns right up in the middle of the canopy. And the reason for that is we've got a very dense canopy here. So what we see is the first returns have come from the upper envelope of the canopy. Then we've got a second level of structure in the canopy there. And because it's so dense, we've got a lot of last returns there. So that means that for the pulses associated with the first and last returns, no more energy made it through to the ground and then back out again. So in this case, it's not true to say that last returns are ground returns, because clearly they're not. However, ground returns are a subset of last returns and single returns. Intermediate returns, as you would imagine, they're somewhere in the middle. Single returns. So single returns are also quite interesting. What they tell us is they had a clear path to their target and back to the sensor. So in an open, let's say we're surveying a parking lot or the top of a building, we're only going to see single returns in those environments because there's no other material that the pulse has encountered. Now in a canopy environment like this, it's quite interesting because we know that there's canopy all the way through here. You know, if we look back to the previous slides, we know that there's canopy all the way through. So what do the single returns tell us here? Well, they tell us that the canopy here is much more open, because the fact that we have a high proportion of single returns at the ground level means they must have made it all the way through the canopy and all the way back out again without encountering other foliage. But in this area, we get very few ground returns that are also single returns or single echoes. So clearly, this is a very dense canopy. So the echo classification tells us something about the fractional coverage, as does the intensity. I'm not going to get into that discussion right now, but I just want to highlight the point that echo classification or return classification and intensity tells us a lot about canopy structure, more than just the point coordinate. So when we're dealing with point clouds, it's important to realize that it's not just where that point cloud is in space. There are other attributes associated with that point that tell us very useful information. So yes, the coordinate's useful, but also the intensity and also its echo class. These are all three very important attributes, and we should use them in models. And so how do we develop models? And this, 1 or 2 minutes. I'm almost done. I just wanted to illustrate how we can utilize the data in generating the model. Earlier I mentioned biomass modeling in Nova Scotia. Well, how do we do that? And I'm not going to go through that presentation. But we get a point cloud in the canopy. That point cloud, this could represent a PSP, or a permanent sample plot. Now, how do we represent that and turn it into something that we can use to model across a stand or across a much larger area? Well, what we see here is that we can convert that point cloud into a frequency distribution, or a cumulative frequency distribution. And then we can extract statistical metrics that describe this point cloud. Now here we can see a signature. These are signatures of different forest classifications, different species classifications. And then we can use these signatures and the associated statistical metrics to construct models, 1, 2, 3 variable models from those statistical descriptions. And then we can apply them over a much wider area. So here, for example, in the top right-hand corner, we can see a species classification from a forest resource inventory database. And just below that, we can see a LiDAR model of exactly the same thing. Now, of course, they don't match up perfectly, but to be honest, I don't know how accurate the FRI data is in the first place. It's debatable as to which one's more accurate, the LiDAR or what's in the FRI. Who knows, and I'm not trying to argue one way or the other. But the point is that we can generate these statistical models from the point cloud and then apply them spatially. Fusion is a piece of software developed by the United States Department of Agriculture, Bob McGaughey. It's freely available, and this is one of the tools that you can use to extract all of those metrics and then develop your own models. I'm not going to talk about that, but just to be aware that there are tools out there for free that can allow you to do this. Canopy density analysis, voxelization of the data. Essentially, this is just counting the number of points within voxel space. Let's say we take a 1 meter by 1 meter by 1 meter cube, count all of the points in there, get the density, and then generate a 3-dimensional voxel space. And we can use, again, canopy density as another mechanism to create models of canopy attributes. Last slide. Okay, so to summarize the whole talk, what's the outlook for LiDAR? This is a very difficult thing to do in one slide, and these are my own opinions, so don't take these as gospel. But I think it's fair to say that airborne LiDAR technology is improving. That means it's getting faster, it's getting more accurate, and the really good one is, I think it's becoming more cost effective. And that's as much the service providers and the manufacturers' fault as it is the end users. The more end users adopt, the more the costs come down. The application demand and the end user community is still growing. Hopefully some of the more esoteric applications that I've illustrated could become more mainstream. And, so that's one area of potential growth. We've seen that the market for LiDAR data and services is around about $500 million per year at the moment. And based on previous trends, it tends to be growing at 10 to 20% per year. Now, the USA market value, based on that cost-benefit analysis that I illustrated earlier, appears to be in the billions, anywhere between 1 and 13 billion if you take the USGS estimates. But that's potential, that's not realized, that's just market potential. And the reason that potential is not met is, again, because of the end user community. In Alberta, just to bring this a little bit closer to home, there's vast market potential. Alberta is very fortunate to have been proactive and have vast stores of data that is available to it. And so, there's a number of applications that could be further exploited. And I've just listed a few off the top of my head. Natural resources and energy assessment, water, forest, minerals, oil, gas, they're obvious ones. Transmission line, placement, monitoring, regulation, hazards mapping, flood slope ability, avalanche. I know there's a lot of academics looking at all of these, but whether they're being implemented is another question. Precision agriculture. Now, this is one that's actually been highlighted a lot in the US. It hasn't been realized yet, but there's a lot more study needed on precision agriculture and how that can be implemented in an operational way, or how LiDAR can be utilized in that way. Urban highway development, obvious examples. So it's fair to say that the community in general, from manufacturers to providers to end users, is maturing. Things are becoming more consistent, but there are still inconsistencies in workflows. Areas of the community still do things in their own idiosyncratic ways. Now, what that leads to is that there seems to be a need for standardization in some areas. There needs to be guidelines. Currently isn't any certification associated with LiDAR. But if we implement standards, guidelines, and certifications, we can probably improve some of that consistency and help with the accessibility of data and maybe improve workflows for end users. So maybe I should have put this slide up first, because I think, in my mind, this explains LiDAR in a nutshell. So I'd just like to leave you with that one. Thank you very much.